Okay. Hi, everybody. Today we'll be starting off with a warm-up question. A pendulum of length 1.8 meters, actually even better. Let's toss out the number. A pendulum of length L exists on Earth. We weren't going to get a numeric answer anyway. Our answer to this problem is going to be an equation, but let's just make it all equations so that we solve this out in the most general way. But a pendulum of length L exists on Earth. What is its maximum velocity as it passes through the equilibrium position as a function of the given variables? And oddly enough, all we need is the length of the pendulum L and the angle theta. Now, this question is kind of hard mathematically. Conceptually, it's straightforward though. Do your best with it. Do your best with it. And there's a good reason why I want to talk about this question, but if I reveal it now, it'll make the answer to this question a little bit too easy. Give it your best shot, then we'll talk about it, then we'll go over it. And then today we'll be doing the tutorial for the free response that was due last night. And we'll be doing the tutorial for the Unit 4 free response, which is all about conservation of energy and the work energy theorem. How's it going out there? Yeah. Have you all been keeping up with your exercise?
Yeah, try to do it every day.
Or
Yeah, that's good. It's super important that you do that. Not just because you're like at the age where exercise is most profitable. Like right now at this age, you will probably get the most muscle gain or weight loss in terms of your input energy. But also, you know, once life gets back to normal, everybody's going to be super different. You might as well come out on the other side like rip, you know? Yeah, come out. Yeah, it's like we either come out like as a regular potato or like cut like a crinkle cut fry. You want to come out on the other side as like a crinkle cut fry. Okay, so a pendulum swings back and forth. A pendulum exists on Earth with length L. What is its maximum velocity as it passes through its equilibrium position? And so what equation do I want to start with here? And can I get a starting equation for a pendulum? What should I begin off with?
Is it the t equals 2 pi square root L over D?
So we have an equation for a pendulum which says the period of a pendulum is going to be equal to 2 pi multiplied by the square root of L over G. And you've activated my trap card. So the reason why we're starting off with this equation, why I would push you towards this, is that because of the way that the AP test has been graded in past years, where you're given points for writing down correct equations with no incorrect equations, there will be cases where they are probably attempting to mislead you. So while this is a true equation for this physical scenario, this isn't going to provide us any useful information here whatsoever. This is only going to tell us how much time does it take to go from here to here and then back, right? And if you had like the distance and you divided it by the time, that might give you a bad approximation of the velocity. But the reason why that just won't work is that distance divided by time makes the assumption that you're moving at a constant velocity, but that's not the case here. This is constantly changing. Here, what is the velocity of a pendulum once it's reached its maximum height? How fast is it moving right here? Yep, right there at the top, the velocity is equal to 0 because it's changing directions.
Oh yeah.
And here, the velocity is at its maximum. So this is to say, and this is a really important lesson to take away, if the acceleration is not equal to 0, then you cannot just say that the velocity is equal to distance divided by time. This is a more complicated equation if the acceleration is not equal to 0. So the velocity is changing. There is some sort of acceleration. That acceleration is probably coming from gravity. And as a result, we can't just do distance divided by time. And so this right here, this is actually not a useful relationship. Now, if they give a question about a pendulum, I bet that if this is part 1 or whatever, that this might be useful for part 2 or part 3, but this is not necessary here at all. In fact, in order to calculate the maximum velocity for this thing, we only really need one relationship.
Is it the third kinematics?
You could use kinematic equation 3 if you knew what the acceleration due to gravity was, or sorry, what the acceleration was, but you don't, because the acceleration is going to be a combination of weight and tension, and unless you can write out a clear expression for A, kinematic equation 3 isn't very useful. What section are we reviewing this week? Conservation of?
Energy.
Conservation of energy and momentum. So this is a conservation law question. Are two objects colliding with each other?
No.
No, so it's not momentum. So this is actually conservation of energy. And here's the deal with this question. Like I said, when an object falls down due to gravity, conservation of energy is going to hold. It doesn't matter if the way that it falls down is perfectly straight down a flat ramp, or down a parabolic ramp, or through a loop-de-loop in a roller coaster and then flat. No matter what, conservation of energy is going to hold. All that matters is what? What is our gravitational potential energy equation?
MGH.
U is equal to mgh. Now, when you pull this pendulum back, assuming the length of the string doesn't stretch, right? The act of pulling it back while keeping this length constant is going to take it and it's going to lift it up oh so slightly. So you're going to lift it up some tiny amount here, some little bit, h, right? And then as it falls, conservation of energy still holds, even though this is following the arc of a circle and not just falling straight down. This is being given a certain amount of potential energy when you lift it up because you are lifting it up slightly from the Earth's surface, imparting it with this little bit of gravitational potential energy. And then as it falls back down to the bottom where the h is 0, what does this become?
Kinetic.
Kinetic energy. So this is going to become equal to 1/2 mv squared. So let's go ahead and start off by solving for the velocity v. So mass doesn't matter, which is why the mass of the pendulum wasn't offered, it wasn't given, right?
Mm-hmm.
And then we can solve for v, so 2gh is equal to v squared. So the maximum velocity reached by the pendulum is going to be v is equal to the square root of 2gh. But what was the request? What did we actually want or need?
The maximum velocity as it passes the equilibrium.
This is the maximum velocity. That is what we just calculated. This is saying that the maximum velocity that the pendulum reaches as it swings through the bottom, where all of its energy is kinetic, is based off the fact that its potential energy being transformed into kinetic energy. And when that happens, the velocity will be this. However, notice the variables given. Is there an h here?
Yeah. Isn't it the H where you like lift it up?
Sure, the H is here, but in terms of the variables given in the question, I added this.
Oh.
Variables given in the question, we have thetas and we have L's. So what we need to be able to do is we need to be able to define this right here in terms of L's and thetas, which we can do if we apply a little bit of trigonometry. So I'm going to draw a straight line over from where it was lifted up to, and I'm going to toss down a right triangle here. Is this okay?
Mm-hmm.
And so what I'm going to do is I'm going to use this theta to solve for this adjacent side right here. What trig function do we want if we're going to solve for an adjacent?
Cosine.
Cosine.
Cosine. So this blue length that I highlighted here, notice it's not the full length L. I'm just going to call this A for right now. This is to say that cosine of theta is equal to adjacent A divided by the hypotenuse. And how long is the hypotenuse of this triangle? How long is it from here to here? It's one of the variables that we've already defined, one that we've been given. What is the hypotenuse of this? It's a pendulum.
Is it L?
It's L. When you pull the pendulum out sideways, the length of the string doesn't change. So cosine theta is equal to A over L. So if I want A, right, I'm going to multiply both sides by L. So L cosine of theta is going to be equal to A. So what is H? How do I get this from the terms that I've defined? How low was this hanging before? Originally, what height does it sit at? How long is this?
The L plus A?
So originally it was sitting at L, and now I'm saying that if I lift it up, then the vertical component is just A. So to get what H is, it's the difference of the two. So the H must be equal to the length it was sitting at before, L, minus A. So this is the same as saying the height that it's going to sit at is going to be L minus L cosine theta, which has the nice feature of, hey, I can factor out an L. So the height that this sits at is going to be equal to the length of the pendulum times 1 minus cosine of theta, which is just the angle that we're pulling the pendulum back to. And so this right here is a famous solution. This is just a pre-solved equation that gives us the maximum velocity of a pendulum based on the length of the pendulum and the angle that it is pulled back to. The maximum velocity of any pendulum on Earth is going to be equal to the square root of 2gl, where L is the length of the pendulum, times 1 minus cosine theta, where theta is the angle that we pull the pendulum back to set it in motion. This equation has the nice feature that the further you pull it back, the higher the velocity is, except it scales non-linearly because it's scaling as the cosine of the angle. And it has the nice second feature that both positive and negative angles work because cosine is an even function. So the velocity that you get is the same if you talk about pulling a pendulum to 15 degrees versus pulling a pendulum to negative 15 degrees. And again, the main point of this question here is, one, to remind y'all that conservation of energy works no matter what the shape of the pathway is. Lesson 1. Lesson 2, just because we have an equation in pocket for a given situation doesn't mean that it's necessarily appropriate for every part of that question. Just because it's about a pendulum doesn't mean you go straight to the pendulum equation. This question had nothing to do with the period. We just wanted the max velocity, which is a common case to apply the conservation of energy. Are there any questions on today's warm-up? No? Okay, so are you all ready to go through the Unit 4 free response tutorial? Yeah? Okay. Okay, so that's that for the physics. Okay. And now the Unit 4 tutorial. So this is Unit 4. Question 1. And before we start, are there any like general questions about the class, current assignments, what we're up to, where we're headed?
How many more FRQs are we gonna have?
That's a heck of a question. Two. There's two more, and then we're done. So all we have left is the Unit 6 free response question and the Unit 7 free response question, which we'll do those two next week, and then we'll be done with FRQs assigned as homework. And then after that, all I have for you is a one final sample test that I'm going to write myself and give to you. I'm going to take my own best crack at trying to guess what their test is going to look like, but of course it's only going to be a guess. We'll do that during a class period so that we can simulate the test conditions, the amount of time that you'll have, the resources that you'll have available to you, etc. And then we'll be done. Yeah, so two more free responses for homework next week, and then one sample exam that I'll write myself and then grade and get back to you probably the week before the test. And then for that week of the test, I'm not going to plan anything for you. I figure since you have multiple APs and it'll be AP week, you do what you will with your time the best way you can spend it. Though I will still hold this Zoom meeting during that week of AP testing that like, let me look at the thing. So we'll be done next week with review. We'll be wrapped up by the 8th of tutorials. And then that week after is when APs start, right? They start on the 11th. Yeah. So that whole week of the 11th up until the 22nd, I will still hold these Zoom meetings in case y'all have questions or you want to roll up and talk or whatever. But for those entire 2 weeks, I'm just going to mark everybody present in the attendance. So that if you slept late because you had an AP test the day before, or you want to cram for whatever you actually want to cram for, so that you can do that uninterrupted with a longer chunk of time. Also, I'll be hella real with you. I have a final that same week too, so I will also be using that time to study. I have a final on, our AP test is on the 14th. I have a final on the night of the 13th that I have to cram for. So I will be available that morning, but in the afternoon, I'll be disappearing that whole week to go cram and study. I have one final to take, a final presentation to give, and then a comprehensive exam to take.
Oh my gosh.
That is fine. Nonetheless, let's go ahead and start now with the Unit 4 tutorial, question 1. So we have two different rockets that we're being told about, right? And both of these rockets are launched upwards with a velocity of v0. They reach the maximum height at time t1, and then they hit the ground at some time t2. And this is AP Physics, so they tell us right off the top that frictional forces are considered to be negligible. Students make predictions about the motion of rocket Y compared to that of rocket X. And I believe when I read the question, the only difference between them is the mass, right?
Yeah.
Yeah. So rocket Y is more massive than rocket X. And so we're given some sample responses from these students. So student 1, rocket Y will have a smaller maximum vertical displacement than rocket X, although it is launched upwards at the same speed as rocket X and has more kinetic energy than rocket X. Because rocket Y will have a smaller vertical displacement than rocket X, I predict that it takes less time for rocket Y to reach the ground compared with rocket X. Student 2 says that rocket Y will have the same maximum vertical displacement as rocket X because both have the same kinetic energy. Since both rockets will have the same maximum vertical displacement, I predict it will take both rockets the same amount of time to reach the ground. And so just to start it off, before we even get to the part where the questions are being asked, both of these students are wrong. And both of these students are wrong for different reasons. One of them is drawing the correct conclusion for the wrong information. The other one is drawing an incorrect conclusion, even though some of his information is correct. So I'm just going to start off with like how I think about this, and maybe it's because, you know, this is my major. I've been doing this for so long. It's really easy for me to pick apart what they're doing wrong. But in this type of question, for like other questions, it's easy to look at context to try and get the answers. For this one, there is no context that can give you the answer other than being able to solve it from first principle. So questions of maximum height, all of that stuff, what are those questions of? Like, what section of the book does that come from? We launch an object upwards and we measure something about it. That's all what?
Is it projectile motion?
Yeah, it is projectile motion. And try and remember, what part of the class were we doing projectile motion in?
The beginning of the year.
The beginning of the year when we were still doing kinematics, right? We weren't even to mechanics. The reason why we were able to do that is that projectile motion doesn't depend on mass. So it literally does not matter what the mass of the rocket is. If these are both shot upwards with the same initial velocity, same trajectory, and all I mean by trajectory is like their angle, and in this case the angle is 90 degrees because they're shot upwards, means that both of these are going to be in the air for the same time and the exact same height. So both of these rockets, if they have the same initial velocity, they're both going to go up to the exact same height. So that's why part A1, student 1 is wrong. They're going to have the same height. And you could justify this all sorts of different ways that you want. You could say that projectiles have, projectile motion is independent of mass. But the easiest way to do it, I think, is to do it with conservation of energy. When it leaves the ground, right, we have 1/2 mv squared of kinetic energy. And when it reaches the maximum height, all of this kinetic energy becomes what kind of energy?
Potential.
Potential energy, mgh. And what do you notice about this setup?
You cancel the mass?
The mass is irrelevant. It doesn't matter what the mass of the object is. The maximum height of any given object is going to be 1/2 v squared over g every time, no matter what. This is all that there is to determining the maximum height of a projectile. So we go on to item 2 now. Oh, I'm sorry. This is part A, 1 and 2. Which parts are correct, which parts are wrong. So the part that is correct is the part where they compared the kinetic energies. They are right. Rocket X will have more kinetic energy. So A, 1 and 2. So Rocket X has more kinetic energy, but he's wrong about the height. And then for the next part, they ask us to talk about student 2's reasoning, which parts are correct, which parts are wrong. So which part is correct for student 2?
The part that they'll have the same displacement.
That is correct, yeah. So again, based on their knowledge of projectile motion, yeah, they should both reach the same height, but which part is wrong?
That they would have the same kinetic energy?
They actually have different kinetic energies, yeah. But it makes sense that, hey, they're going to get to the same height, even though they have different kinetic energies, because the rocket that is more massive proportionally will need more energy to get to the exact same height. So student 1 has the correct description of energy, but the wrong conclusion. Student 2 has the correct conclusion, but the wrong rationale behind it. Item B, use quantitative reasoning, including equations as needed, to describe expressions for the maximum heights achieved by rockets X and Y. Express your answers in terms of V naught, MR, G, and other fundamental constants as appropriate. So, oh my God, my numbering is so bad. Why am I so bad? I'm sorry, this isn't B, this is 3 and 4. Okay, 3, 4. Okay. Now item B, derive the maximum height equation. So yeah, straight up conservation of energy. And it's a little bit of a red herring because the mass is irrelevant. So this has 1/2 mr v naught squared is equal to mgh. Yeah. Where it doesn't matter, this proof is going to be the same for both. They both reach the same height. That's provable by conservation of energy. H is just going to be equal to v naught squared over 2g. That's everything for determining the max height. Of course, this isn't how rocket science actually works, because a rocket doesn't start off with all of its initial velocity. It slowly accelerates up to its speed. So in order to actually get the height of a rocket, you have to do a calculus.
Mr. Rob.
Yes.
I remember on your notes, like we derived the equation for rockets, I think with ln. That would they ask us this on the AP test or no?
No, that was for your own enrichment.
Oh, okay. All right.
Yeah, no, never. Heck no. Yeah, the actual rocket equation, you could just Google the rocket equation, and yeah, it has natural logs in it. I just wanted to show you all that, to show you like why it is what it is, and to show you a little bit of exposure to differential equations.
All right. Okay.
That was actually the first differential equation that we solved before we solved the differential equation that lets us do all of the period equations.
Mm.
Yeah, and that stuff's good to know anyway, because differential equations are on the AP calculus test. Maybe not ones that hard, but they're on there. Anyway, item C. We want to figure out how much time it takes to reach the ground after reaching their respective maximum heights. And again, how do we do this? This next part is just old kinematics. So we're starting from a height h. And how much time does it take for an object to fall from height h? Which kinematic equation do we use?
Can we use the second one?
We have to use the second one, yeah. So the first one doesn't have any information about height. There are no distances there. The third one doesn't have any information about time, so that narrows it down to kinematic equation 2. So that is to say, x must be equal to x naught plus v sub o t plus 1/2 at squared. But when we're talking about falling, what provides our acceleration?
Gravity.
Gravity. T squared. When we're at our maximum height, the velocity is 0. So I'm going to toss this away because we're starting from that top position. So that is to say, x minus x naught, our displacement will be equal to 1/2 gt squared. And if we're falling, what is our maximum displacement? We're falling from where down to 0? We're falling from where down to 0?
Height h.
We're falling from height h. H is equal to 1/2 gt squared all the way down to 0. Solve for t, and this will give you the amount of time it takes to fall once it's reached its max height. So this is 2gh square rooted will give us the, will give us the time of flight. And again, this is without respect to mass. And then, yeah, we already did this. I guess we were doing this the whole time as we went along. Explain how this relates to whether or not they're right or wrong. Despite the fact that, you know, you'd also have to consider the kinetic energy equations. Kinetic energy is equal to 1/2 mv squared. So that is to say the kinetic energy of rocket X is equal to, which one was heavier, X or Y?
I think Y was heavier.
Yeah, Y was heavier. So 2 times the kinetic energy of rocket X is going to be equal to the kinetic energy of rocket Y, just because it's double the mass. So this is just saying that this is 1/2 mv naught squared. And this other one is 2 times that, right? Because it's 2 times the mass. Despite the fact that one has double the kinetic energy of the other, that is a correct statement. They reach the same height and they fall back to the ground with the same amount of time, because in the relationships that are determinative of the max height or the time of flight, the masses cancel out in such a way that they have no impact on this value or this value. That's the physicsy way to talk about it. Are there any questions there on free response 1 for unit 4?
So there's the only difference is their kinetic energies, right?
Yeah, one has double the kinetic energy of the other, but the one that has double the kinetic energy also has double the mass, so it's going to take twice as much energy to carry it upwards to the same height.
Okay.
Wait, Mr. Rob,
Yes.
that equation for C, when you were isolating for T.
Well, item C. Okay.
Yeah.
Yes.
When we were isolating for T, so the algebra is just you multiplied over the 2, and then.
Oh, yeah, a mistake was made. Going too fast here. So this is 2h over g.
Okay, all right, yeah.
Yeah. Multiply by 2, divide by g. So 2 capital H all over g is equal to t. God, don't tell that to the people reviewing my grad school test. Jesus Christ. Of course, I only made the mistake because I did it with algebra. If I did it with calculus, it would have been immaculate and gorgeous. Is this okay?
Yes.
Okay. And then item number 2, which I really like because I think I've told this story before about the one thing that got me into physics. Have I told you guys about like why I decided to major in physics when I was a junior in high school?
No.
Oh, word. Okay, let me tell you guys a story that's too long, okay? Let me take this and move it. And this has a lot to do with the next free response question, so it's a question worth thinking about. When I was a lad of the bright young age of 17, when I was like 13 years ago, our AP physics teacher was like, all right, we got a lab because we just learned a little bit about conservation of energy. And here's the lab. You need to make a bungee cord and attach it to the ceiling of the classroom. And that bungee cord is going to be made of rubber bands. So you have rubber band, rubber band, rubber band, rubber band, rubber band, rubber band. You're given the height of the classroom, some capital H. And what you need to do is you need to figure out how many rubber bands need to be in this chain, so N rubber bands, such that you can then attach an egg to the end of this. Egg with a mass of egg, right? So I'll just call it M sub E. And the job is to take this thing and lift it up to the top of the ceiling here, and then drop it so that it falls all the way down to the ground and touches an ink pad. And you get a C if the egg cracks. If you short it, if the egg doesn't touch the ink pad at all, you get a B. But there's only one way to get an A, and that is to drop this from the top here, let it fall, 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 and then touch the ink pad and print a little bit of ink on the egg, but the egg doesn't crack. So that's the only way to get an A. And this isn't an engineering project, so you couldn't do this by trial and error. You couldn't just like try more and more and more and more and more rubber bands. You would actually have to do this from first principles. So just use what you know about physics in order to calculate it. And the only materials you were given to do the math are one of the rubber bands that are going to be used to make the daisy chain.
Oh.
Is that okay?
Mhm.
So what relationships are here? Like, what do you want this system to do? How would you set this up in order to solve for the number of rubber bands N?
Mm,
So we're going to let the egg fall, and like I said, it's not falling from here, it's falling from the maximum height up here at the ceiling, and it's going to fall down to the ground. So what kind of energy relationships are going on there?
Is that gravitational potential energy?
So the egg has some amount of gravitational potential energy. U is going to be equal to mass of the egg, G times H, the height of the classroom. And if there were no rubber band in the way, what would this energy become?
Kinetic
Kinetic.
energy.
Become kinetic energy, and your egg would accelerate towards the ground, achieving a velocity of v, right?
Yes.
Where if you allow this to go forward, this is going to become kinetic energy is equal to 1/2 mass of the egg, v squared. And then when it achieves that velocity and touches the ground, you get a bad time, right?
Mhm.
You get that c. However, because it is attached to the bungee cord effectively, what is going to happen to that energy instead? Instead of all becoming kinetic energy, it's going to be subverted and become what?
Potential.
What kind of potential?
Is it spring potential?
Elastic?
Yeah, it's exactly that. It is spring elastic energy.
Okay.
And so when you do that, right? Instead, we're going to say, I don't want this to happen. Instead, I want this, and this is true of actual bungee jumping, kids. I want my gravitational potential energy to be subverted and become spring potential energy instead. So potential energy of a springy rubber band, which is equal to 1/2 k x squared, right? The amount of stretching that it is going to receive before it hits the ground. So the goal is so that here the velocity is equal to what? What do we want the velocity to be when it touches the ink pad?
0.
0, yeah.
Yeah.
Okay. And so here is the part where it gets hard. This is the part that got me addicted to physics. This is an easy setup. However, we have to make 2 wild substitutions in here in order to get a good answer. And so basic setup, mass of the egg, GH, is going to be equal to 1/2 kx squared. Mass of the egg, well-defined. G, well-defined. H, well-defined. 1/2, well-defined. K, not well-defined. X, not well-defined. Here's why, and I'm going to do a little bit of setup here. Let's say that you have 1 rubber band, right? And N is the number of rubber bands that you are going to need here, right? Let's say that the length of 1 rubber band is L. What is this X? What is X in the kinetic, or I'm sorry, in the potential energy equation for a spring?
Isn't that how far the spring's pushed back?
That's how far the spring is stretched. And now when the rubber band is unstretched, it's going to have some like fundamental length, right? And so only this amount from where the rubber band hangs naturally when it's not being stretched down to the ground, this is actually going to be our amount of stretch. This is going to be our actual X here, right? Does that make sense? Like the rubber band has some length and we're only counting the length of it getting elongated. And so what I'm going to do here is I'm going to say N is our number of rubber bands. L is the length of 1 rubber band. So this part from here to here, that's going to be N times L. So the total height of the classroom is going to be equal to N times L, which is the length of our rubber band chain, then plus X, the amount of stretching that it's going to go through. And so I'm sorry, we're solving for X. X is going to be equal to the height of the classroom minus the natural length of the rubber band chain, minus N times L. So that's one thing that we would have to substitute in here. The other thing that we would have to substitute in here is the fact that, and this is no longer part of the contents for the class, but what I'm about to talk about used to be part of the class. What happens if you have multiple springs? Because each one of the rubber bands is going to act as its own spring in this setup. And it turns out that when it comes to doing engineering, if you're actually making devices that have multiple springs, there are different equations for adding the way that the springs are combined. Sorry, I'm trying to find this good slide that shows the 2 equations. Here's a good look at it. And what I'm about to show y'all is like college stuff for engineering. But when you take a bunch of springs and you put them together end on end on end, we have different equations for determining what their new spring constant is. So if you have 2 springs in parallel, right, 2 springs side by side, it's effectively going to make 1 new spring, which has the stiffness of both. So if you put 2 springs side by side and you want to know what's the new spring constant, that's easy. You just add them together. If you want to overcome the force from the spring, you have to overcome both of them. But if you put springs end on end on end on end, like this, right, then the equation to get the new effective spring constant is more complicated. It's going to be 1 divided by the total spring constant is going to be equal to the sum of 1 divided by K for all of the other spring constants. So I'm going to solve this out, and this is a gnarly thing, but like I said, this is my like dumb story of what got me into physics, like this solution being particularly elegant. So this is how you add up the spring constant for a bunch of different springs, where one of these Ks, right, this K is how the whole daisy chain will behave together, but each of these Ks is the K constant from 1 rubber band. Well, if you add this up for all the rubber bands you put end on end on end on end, and I said that I'm going to have N of them, there's going to be N springs here in my daisy chain, then 1 divided by the total spring constant is going to be equal to N times 1 over K, because if you added up N of these, it would just be N times that. So now I can reciprocate both sides. So the spring constant of how that thing is going to behave is equal to the spring constant of one of the rubber bands divided by n. And so I plug in these two things, right, where I've defined these in terms of variables that are already in the problem. So mass of the egg, g, height of the classroom, is equal to 1/2 spring constant k, where this is going to be how it behaves. And oddly enough, the more rubber bands you put on there, the weaker of a spring that it behaves as. So the spring constant of one rubber band, which you would have to test for experimentally, divided by the number of rubber bands n, then multiplied by x squared, where this is x, the distance that it's going to stretch based on the height of the classroom and the natural length of the rubber band chain. So h minus n times L squared. And what were we solving for in the first place? What was the point of the lab? What were we trying to determine? How many what?
Rubber bands.
How many rubber bands? So you take this relationship, this very fancy one that we built out, and you solve it for n, which it's quadratic, so it'll take a little bit of work. You have to take this part here, square it, divide by n in all of the terms, and then you can solve for what n is. And if you plug in all the other values, it was like magic. Plug in the mass of the egg, the height of the classroom, the spring constant of one rubber band, and h is reused, also L, the average length of a rubber band. You do this, you solve it for n, and this egg will perfectly kiss the ink pad without cracking or breaking, and you get an A.
Oh.
It's just a lot of thinking and conservation of energy statements. Anyway, so all of that set up, working out a completely different problem, just to talk about this second question here. An amusement park bungee jump ride, right? So we get on this bungee jump thingy and jump, and an amusement park ride is designed such that one end of an elastic cord is fixed some distance d above the ground. The person jumps down, and we're given the unstretched length of the cord L. And as the person falls, the elastic cord stretches, and we're modeling it as a spring. When the person is at the bottom of the ride, their head is a distance h above the ground, right? So what we need to do here is same as we did here, but probably with slightly easier math than this. We need to set up the necessary equations. So when the person is at the top, they have some amount of gravitational potential energy.
Mm-hmm.
And they're starting off with some mgd because they're saying that this is d. We have our bungee cord. We have our person, who I don't want to draw, so they're just going to be a mass m. And they're going to fall until they are a height capital H above the ground. So what we're looking at here is that at the beginning, we have some amount of gravitational potential energy. We have mgd. And then when we fall, are we going to get to a point where we have 0 gravitational potential energy?
No.
Yeah. Right.
Wait.
No, you never get to 0 because you never get to the ground. If you have 0 gravitational potential energy when you're bungee jumping, you have died because you have impacted the ground.
Oh no.
And so this is going to be equal to mgh, the amount of gravitational potential energy we have when we're at the bottom, plus what?
The spring
Potential.
Plus the spring potential energy.
Yeah,
So plus 1/2 k, and the amount that it stretches, I think we had a number for. The cord is an unstretched length of L. So we'll just say that the distance that it stretches is x, yeah? 1/2 k x squared, where x is the stretch length. And just like before, how we had to think about, well, like, okay, when it's not stretched, the bungee cord has an inherent length of L, right? So right here, we have our inherent length of the cord L, but we're being stretched this amount x. Notice, because of all the ways that these lengths line up, we can actually use x and redefine it in terms of what's here, right? So notice here, the total height of the platform is d. Here I have L, and here I have h, and x is what's in the gap. So is it fair that the natural length of the spring L plus x plus h, all three of these add up to d, right?
Mm-hmm.
And so the one here that I needed to get so that our equation here would be in terms of only what was given, we need to isolate x. So that is to say x, the amount that the bungee cord stretches, must be equal to d minus the quantity of L plus h. Just subtracting L and h over to the left-hand side. And now I can take this and I can plug it in. The other nice mathematical move I can make is I'm going to subtract mgh to the left-hand side. And that is due to what fact? Why would I do that? Why would I do that? Why would I move these over here to the left? What's nice about that?
They both have mg.
Yeah, so these both have mg. So it's going to be mg times d minus h, which is to say, how far do you fall? D minus h, you're falling this total length here. And this is going to be equal to 1/2 k multiplied by the stretch of the spring squared, where x is justified geometrically as the distance that the string stretches, d minus L plus h, then quantity squared. So this is probably overkill for this step. The only reason why I would do this is because it's going to make this next part easier, a little bit more straightforward. For the second part, they then ask us to derive an expression for the spring constant of the cord, which is easy because since I wrote it this way, this will give us K. So at the top here, we have potential energy due to gravity. At the bottom here, we have potential energy due to the spring. And in the middle, we have kinetic energy, just to like round out all of our thinking on part 1. And then for parts 2 and 3, part 2 here, solve for K, isolate K. So that'll be 2 mg d minus h, then divided by this stuff, d minus L plus h quantity squared. This is equal to K. This is why when you actually go bungee jumping, notice the mass does matter. That's why they measure your body weight before you bungee jump and give you the appropriate cord. The rest of this is constant for the particular bungee jump that you're doing, but your body weight is significant in this calculation. And so usually they have 3 or 4 different cords for different body weight ranges, just to make sure that the ride functions properly. And then finally, B, suppose the air resistance cannot be ignored. For the position at which the person has jumped from the platform, the cord reaches its maximum stretch length. How does the stretch length of the cord in the case with air resistance compare with the stretch length in the case without air resistance? So now include air resistance. Does it stretch more or less?
Less.
Why less?
Because energy is lost, right?
Very good, and that's the easiest way to state it. So with air resistance included as a significant part of this action, so with air resistance, the amount of stretch, which I called X here, we got less stretch, and that is simply due to the fact that instead of all of the kinetic energy becoming potential energy in the spring, it's the kinetic energy minus the energy lost due to air resistance becoming the potential energy. And so that's it for tutorial on the Unit 4 questions. Work on that Unit 5 stuff, and tomorrow we won't start the tutorial on it because it's not due until tomorrow night. So we'll do the tutorial for that Friday. Tomorrow when we come in, we might have a slightly shorter class than normal in case you guys want to plan a second thing to do this hour. I'll just check in, we'll do a warm-up, touch base, see how you're doing. And then I'll take your questions, but if there's no questions, we'll head out early tomorrow. Does that sound good?
Yep.
Yeah.
Okay. Y'all have a nice day. Keep working on that Unit 5 free response question. Only 3 more free responses to go for the whole class.
Okay.
Peace, y'all.
Mr. Rob,
Bye.
Yes?
I was having a little bit of trouble joining the meeting today. I don't know why. I wasn't able to join until I think it was like 11:05 that I ended up joining. Like I
Okay.
kept trying to do it, but it wouldn't allow it.
Okay.
Yeah, I just wanted to let you know.
No problem.
All right. Bye.
Bye.
Bye.